12.2, the law of cosines. So in section 12.1, we have the law of sines, and the law of sines helped us solve for triangles where we were given an angle side opposite pair. What if you don't have an angle side opposite pair to help you get going, and you can't quickly get to an angle side opposite pair? So what if, for example, you're given two sides in the included angle? All right, so you can't possibly get to an angle side opposite pair here unless you know that it's a right triangle. You follow? Or what if you're given three sides of the triangle? All right, this is where we're going to be using the law of cosines. So let's look at the statement of the law of cosines. Once again, we've got the classic angle side opposite pair labeling here. So we've got alpha there, A here, and then we got sides B and C. Law of cosine says a squared is equal to b squared plus c squared minus 2bc cosine alpha. Now the way I like to remember this formula is that if I want to get a squared, I'm taking the sums of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the included angle. That way, no matter how you label things, you'll remember the formula. Now, if you're looking for an angle instead of a side, you can actually solve this for cosine alpha. You'd add things over and subtract things over. You'd get to b squared plus c squared minus a squared over 2bc. So it's the sum of the squares of the other two sides minus the square of the opposite side over 2 times the product of the other two sides. Okay. Now something we'll see later on, and what's nice about cosines is when you go to use the inverse cosine to find an angle, if cosine's positive, it'll tell you it's quadrant 1. If it's negative, it'll tell you it's quadrant 2. In other words, if we're using the law of cosines to find an angle, it's going to tell us if the angle is acute or obtuse. So that sort of ambiguity we have with the law of sines, that's just not going to be here. So that'll make things a little easier for us. Well, like everything else in trigonometry, the proof of the law of cosines comes from definition of sine and cosine on the unit circle, along with the Pythagorean theorem. So this is how we would set about doing this. Let's go ahead and start with our triangle here. We'll make one vertex at the origin. So if I have a, putting alpha here in standard position, if the side of this triangle is length b, then the point here, vertex of this angle would be at the point b comma 0. If I think of this as being on a circle of radius c, I can use what we know going back to section 10.2. X is r cosine theta, y is r sine theta. If I'm thinking of this point being on a circle of radius c, the radius is going to be c. And we've put alpha here in standard position, so that's our angle. Okay? So now we're going to do the same kind of thing we did when we derived the difference formula for cosines. I'm going to calculate the distance between these 2 points, B and C, and set that equal to A. So using the distance formula, which once again comes from Pythagorean theorem, look at the difference of the x values. So C cosine alpha minus B quantity squared, plus the difference of the y values, C sine of alpha minus 0 quantity squared. Now I'll square both sides so as to get rid of that square root, make things a little easier to see. So C sine alpha minus 0 is just C sine alpha, so that's going to get squared, so we're squaring the C and the sine. Here, when we go to multiply this out, we would be foiling it out, so I'd have c cosine alpha times itself. So c cosine squared alpha. We'd have minus bc cosine alpha, and then we'd get another one of those, so minus 2 of those, minus 2 bc cosine alphas, and then plus the b squared. So we're actually almost home, right? We're actually almost home. Let's rearrange things. You see that cosine squared alpha plus sine squared alpha. We know that together those will add up to 1. I've got a c squared coefficient out front. So I'm going to rewrite this as, I'm going to put the b squared first, just for alphabetical order. And then I'll factor that c squared out of the cosine squared term and the sine squared term. And now I just use the Pythagorean identity. Cosine squared angle plus sine squared of the same angle is always 1. And boom, there's the law of cosines. Okay? To get the other variant, once again, you're just solving for cosine alpha. Okay, let's put this to good use here in example 1. Solve the following triangles. Give exact answers and decimal approximations. Like in section 12.1, we'll be using decimal degrees here, so make sure if you're using your calculator or Desmos, you are in degree mode. Let's see what we've got going on here. We've got an angle beta. Beta is given to us as 50 degrees. The side opposite beta we'll call B. And we have 2 other angles left over. We've got A and C, so I'll call that, we'll call that 2 units. So that'll be C, so this will be angle gamma. Then this will be 7 units. I guess I'll call that A. I'll call that alpha then. Right? Doesn't really matter as long as we're consistent. So if we think back to the triangle congruence, right? What are we given here? We're given an angle with, we're given 2 sides in the included angle. So this would be considered an SAS format, right? Side angle side. And so we couldn't use the law of sides even if we wanted to, because we don't have the side opposite B, nor do we have enough information to get either alpha or gamma to get the angles opposite the sides we're given. So we'll use law of cosines. All right, so I'm looking for side B. So B squared equals the sum of the squares of the other 2 sides. The other 2 sides are length of 7 and 2. So it'd be 7 squared plus 2 squared minus 2 times the product of the lengths of those 2 sides times the cosine of the included angle, 50 degrees. So B squared equals 49 plus 4, that's what, 53, minus 14 times 2, 28, cosine 50 degrees. B, remember, represents the length of the side of a triangle, so I just can concern myself with the positive square root. And I can fire up Desmos now and approximate that to hundredths. So once again, check on Desmos that you are in degree mode. We want the square root of 53 minus 28 cosine 50 degrees. So that's roughly 5.92 units. Okay. Now that we've got B, I have an angle side opposite pair. So at this point, we can do a couple different things. We can use the law of cosines to go find alpha and gamma, which we can do. Okay, or we can use law of sines now. Okay. Either using law of sines or law of cosines is going to necessitate us using our calculated value of b. Law of sines is typically easier to go after. Now, you might be saying, wait a minute, Stitzy, if I'm doing law of sines on this, right? Let's say I'm going after, for example, gamma. Using the law of sines, it's an angle side side. Okay? But remember, there's only one triangle here. Okay? So here's what we do at this point. So now that we have an angle side opposite pair, in particular we've got the angle side opposite b and beta, I'm going to use the law of sines. I know there's only one triangle left. Okay? So I'm going to go after the smallest angle because I know that angle has to be acute. So if you think about it, in any given triangle, only one angle can be obtuse. The angle I'm given, beta, is acute. So there's a possibility that gamma or alpha could be obtuse. Instead of getting myself into a big old mess with the law of sines, I'll go after the smaller of the two angles. In other words, I'll go after the angle that's opposite the smaller side. I know that has to be an acute angle. So I'll go after the smaller of the two angles because I know that it's an acute angle. Okay? So here, I know that gamma has to be smaller than alpha because the side opposite gamma is only 2. So the sine of gamma over c is going to be equal to the sine of beta over b. So the sine of gamma is c times the sine of beta over b. C is 2. The sine of beta would be the sine of 50 degrees. And then b is what we calculated here. It's roughly 5.92 units. All right. So let's go through the machinations here. Now what I do is I've got this in Desmos, so I can use this expression for b instead of incorporating any round-off error. So that would give me the sine of gamma, 0.25896, etc. And then gamma is going to be the arc sine of this. I know gamma has to be an acute angle because it's going to be the smaller of the two angles that's left over. So I can just take the arc sine of all of this, once again, without having to do much round off, although there's going to be round off anyway. I'm getting it to be dead on 15 degrees. Okay? And now that I know what gamma is, I can find my missing angle alpha. All right, alpha plus beta plus gamma has got to be 180 degrees. Beta is 50. Alpha is 15. Or excuse me, gamma is 15. So let's see, if I take 180 minus 50, that's 130, 115 degrees. So alpha did end up being an obtuse angle. Okay. So once again, if you're given two sides in the included angle, you can get the third side and do law of sines to get the smaller angle. Whoops. and then you can subtract to get the last angle. Okay. All right, number 2. We're given the lengths of 3 sides. So here we don't have any angles at all. So here we're forced to use the law of cosines to help us find the angles. All right, so let's just sort of sketch this out. Angle alpha 4, angle beta 7, angle gamma 5. Once again, it doesn't matter how you label these things as long as you're consistent. So here's the thing with law of cosines. Remember, cosine will detect obtuse angles or not. So if you're given all 3 sides, I like to go after the biggest angle first to see if it's going to be an obtuse angle. So I'm going to go after angle beta. So cosine of beta equals the sum of the squares of the other 2 sides minus the square of the side opposite over 2 times the product of the other 2 sides. So 25 plus 16 is 41 minus 49. So this is negative 8 over what, 40? Which is minus 1/5. All right. So I know that beta is going to be the arc cosine of negative 1/5 degrees, whatever that ends up being. Okay, in degree mode, I should say. Arc cosine of negative 1/5 in degrees. Notice it's going to be an obtuse angle because cosine is negative. So arc cosine of negative 1/5. Once again in degree mode, 101.54. Okay, that's roughly speaking. There it is. Okay. Now I have an angle side opposite pair, so I can just run off and do law of sines. Once again, it's not going to be the ambiguous case because I know that there's only one triangle here, and I've already identified the obtuse angle. So I don't need to worry about which one I pick. If I want to go after alpha, for instance, go after the smaller of the 2 angles left. Sine of alpha over 4. Excuse me, sine of alpha over A is sine of beta over B. So sine of alpha is A sine of beta over B. We're picking A to be 4. Sine of, I'll just put that in there. Well, actually, it really doesn't matter. These are about the same amount of stuff to write down. Arc cosine of negative 1/5. All over B, which was 7. Okay, so let's see what we get for alpha here. So alpha would be the arc sine of all of this stuff. And once again, I don't need to worry about cases. I know that alpha has to be an acute angle because we've already got the obtuse angle accounted for. There is an obtuse angle. We know what it is. So I need 4 times the sine of the arc cosine. So I need 4 times the sine of the arc cosine of negative 1/5. And that's all divided by 7. And then I need the arc sine of all of that. So I'll just copy and paste that in there. We're getting roughly what? 34.05 degrees. All right. And now that I have 2 angles, I can get the third. Because alpha plus beta plus gamma has got to add up to 180 degrees. So alpha is 34.05 degrees. Beta is roughly 101.54 degrees. Gamma is 180. I should say maybe, technically speaking, right? Gamma is approximately equal to 180 minus 34.05 minus 101.54. Let's go ahead and work that out there. 180 minus 34.05 minus 101.54. So 44.41 degrees. Okay. If I wanted the exact value here, I'd have to put stuff in terms of arc cosine here, and then the arc sine of, what was it? 4 sine arc cosine minus 1/5 all over 7. Okay, degrees. Anyway, that's how you do it. So I guess to keep in mind here, if you start off with the law of cosines, if you have no angles, you want to go after the largest angle, because cosine will tell you if it's acute or obtuse. Right? Once you get down to an angle side opposite pair, you can use the law of sines to go after the smallest angle. Hopefully the logic makes sense. If you're given all three sides and you use law of cosines to get the largest angle, it'll tell you if it's obtuse or not. Then you know the other two are going to have to be acute. If the largest angle is acute, you know the other two have to be acute. When you're doing law of sines, once you've gotten an angle side opposite pair in a law of cosines problem, you know there's just one triangle, you go after the smallest angle because you know that one has to be acute. Okay. So there you go. Example 2 here, a researcher wishes to determine the width of a vernal pond, as drawn below. From a point P to the easternmost point, pond's 950 feet. To the other extreme, it's 1,000 feet. The angle between the two lines of sight is 60 degrees. Find the width of the pond. So we could call that thing W. You notice we've got a triangle here. We're given two sides and an included angle. Law of cosines. So W squared is going to be the sum of the squares of the other two sides. Minus 2 times the product times the cosine of the angle between them. Now, one thing to notice here is that we're going to get, unit-wise, we'll get feet squared from here, feet squared from here, and then feet squared from here. The 2 and the cosine are going to be dimensionless. Okay, so we can go ahead and work this out. So 950 squared plus 1,000 squared, 1,902,500 minus you got 2 times 950 times 1,000 times the cosine of 60 degrees. Cosine of 60 degrees is a half, so I'm just going to get 950 times 1,000. So that's just 950,000. So I'll just subtract those two numbers now. $952,500. W is the width of this lake, so I'm just going to only concerned with the positive square root of this. So 975.96 if I round to the nearest hundredth of a mile. 975.96. Whoops, excuse me. 975.96 miles. Okay. Last topic here in the section is Heron's formula. This is named in honor of a Greek mathematician. This gives us a formula for the area of a triangle given just its sides. And it's phrased in terms of what's called the semi-perimeter. So if you have a triangle here, you got lengths of the sides A, B, and C. The perimeter is what you get when you add up all the lengths. You take the perimeter divided by 2, that's called the semi-perimeter. That's what they're calling S. So Heron's formula says what you do is you take the semi-perimeter and you multiply that by the semi-perimeter minus the length of each of its sides. All right? Now, if the semi-perimeter is measured in units of length, then S minus A would also be units of length. S minus B would also be units of length. And S minus C would be units of length. So when I would multiply all these together, if I just looked at what was going on as far as units go, I'd have the square root of units to the 4th power, which, we know does give it square units, which should be for area. The story goes is that units to the 4th power kind of gave some of the Greek philosophers cause for concern, because you can't really think about 4 dimensions in 3 space, can you? Or can you? How would we go about proving this? Well, if you think back to the last section, we had a formula for area involving the sine. The area of a triangle is 1/2 the product of 2 sides times the sine of the included angle. All right? One way to go about deriving Heron's formula analytically as opposed to just strictly geometrically is to use some identities here. The sine of alpha is the square root of 1 minus cosine squared alpha. Right? That comes from the Pythagorean identity and the fact that alpha is an angle in a triangle, so the sine will always be positive. Now that cosine's involved, I can use the law of cosines to get the side lengths involved. Okay? So we go through this derivation in the book. There's just lots of algebra, lots of simplifying, but that's where it comes from. All right? So let's just work through our one example here. We've got a triangle with side lengths 4, 7, and 5. So I want to find the area here using Heron's formula. First step is to find the semi-perimeter. So that's the perimeter. In other words, that's all the sides added up divided by 2. So I get 16 over 2, which is 8. So the perimeter is 8 units. Then I take S minus each side. So 8 minus 4, that's 4 units. S minus B, 8 minus 7, so that's 1 unit. S minus C is 8 minus 5, that's 3 units. So plug it into Heron's formula. A equals the square root of S times S minus A times S minus B times S minus C. That's 8 times 4 times 1 times 3. And once again, this would be units to the 4th power. So taking square roots here, let's see, as far as perfect squares go, we can bring, there's another factor of 4 in here. So I can bring a 4 out front with the square root of 6 units squared. All right. They don't ask for a decimal approximation, but we could certainly use Desmos to give you one. Okay? And so that'll do it for Law of Cosines.